Hello boys and girls. Today we take up hybridization concept. It's a very important concept. Previously in chemical bonding itself, geometries I gave you in the valence shell electron pair repulsions theory, you can refer, verify all those things, all the geometries of molecules with the change of bond pairs and lone pairs. And today we take up hybridization. What is hybridization first of all? Nearly same or same energetic pure atomic orbitals mix up to form nearly same or same energetic atomic orbitals, pure atomic orbitals mix up to form equal energetic and equivalent orbitals. What are those equivalent orbitals called as hybrid orbitals? Hybrid orbitals of valence shell, right, involve in the hybridization, not electrons, only, right, orbitals of valence shell involve, not electrons involved in the hybridization. And number of pure atomic orbitals participating in the hybridization equal to number of hybrid orbitals formed. For example, in Sp2 hybridization, 1s and 2p orbitals are mixing up and you get 3 Sp2 hybrid orbitals. Similarly, in Sp3 hybridization, 1s and 3p atomic orbitals completely mixing up to form Sp3 hybridization. You get 4 equivalent Sp3 hybrid orbitals. That is what I meant by number of pure atomic orbitals participating in a hybridization equal to number of hybrid orbitals formed. Hybrid orbitals formed will have equal energy and shape, geometry is same, and will have equal energy, all of them. Promotion of electrons is not compulsory, not necessary during hybridization. Okay, then what type of orbitals can hybridize? Half filled, completely filled, even empty orbitals can hybridize. Hybrid orbitals formed will have more effective or stronger overlapping character and form stable molecule. Then hybrid orbitals directed in space so as to have minimum repulsions and maximum stability. So hybrid orbitals arrange in such a way they have minimum repulsions and maximum stability. For example, if I say tetrahedral, that is how they arrange it, because in that state of geometry they have minimum repulsions and maximum stability. Then we have various types of hybridizations: Sp3, Sp2 and Sp hybridizations. What is Sp3 hybridization? One spherical s orbital and 3 pure p atomic orbitals completely mix up to give, you can see, 1, 2, 3, 4 Sp3 hybrid orbitals in a tetrahedral shape. And what's the percentage of S and P character here? Sp3, 1s and 3p. Percentage of S is, right, 1/4 into 100, 25%, and percentage of 25%. Percent of P is 3/4 into 100. Totally P orbitals are 3 out of 4, 3/4 into 100. So this is 75% P character. Similarly, Sp2 hybridization, one spherical s orbital, 2 dumbbell shaped p orbital completely mix up to give 3 Sp2 hybrid orbitals. What's the percentage of S? Percentage of S is 1/3 into 100, right? Percentage of P is 2/3 into 100. And these Sp2 arrange in a trigonal planar shape. And Sp hybridization, one spherical s orbital, 1 dumbbell shaped p orbital completely mix up to give 2 Sp hybrid orbitals in a linear shape. 2 Sp hybrid orbitals in a linear shape. So this is what percentage of, and what's the percentage of S and P character here? 50-50, half into 100, half. So Sp, how to find this hybridization? I gave you in the description. Before, in valence shell electron pair repulsions theory itself, I was giving you how to find the geometry. You can verify that. Finding the hybridization of various molecule, I gave you some equations, some formulae, and even for carbon compounds, How to find, I gave you. Next. Then few examples, let us take few example. Beryllium chloride. Beryllium in the ground state has no unpaired electrons, but beryllium in the excited state has 2 unpaired electrons, and in the excited state only 2s and 2p orbitals completely mix up to give sp hybridization, 2 sp hybrid orbitals. In the linear shape, they arrange in a linear shape with a bond angle 180 degrees. And here sp hybrid, this is sp hybrid orbital of beryllium. This is also sp hybrid orbital of beryllium. Here only chlorines, beryllium's is this. And what about chlorine? Chlorine has 3s2, 3px2, 3py2 and 3pz1. This half-filled p orbital of chlorine. See, chlorine is not hybridizing, only beryllium, only one of the central bonding atom hybridize. Not all the atoms will have. What is the central bonding atom that can form more number of bonds? Is the multivalent atom, one that can form more number of bonds in that structure is a central bonding atom. Here beryllium is able to form 2 bonds. Now central bonding atom in beryllium chloride is beryllium. And now chlorine is not hybridizing, only beryllium is hybridizing in sp hybridization. Half-filled chlorine's p orbital here, overlap and forming spp sigma bond. This side also beryllium's half-filled sp hybrid orbitals overlap with half-filled chlorine orbitals of p orbitals of chlorine and forming spp sigma bond. Now beryllium gain 4 electrons in its outer shell and chlorine gain 8 electrons in its outer shell. Beryllium below octet and linear shape in the excited state. And one more thing is beryllium is divalent. You can see beryllium is divalent or bivalent. What is the reason? Because in the excited state, beryllium has 2 unpaired electrons. That is the reason why beryllium is able to form 2 covalent bonds are divalent. So overall beryllium chloride is linear in shape. 180 degrees is the bond angle. Beryllium undergoes sp hybridization. There are 2 sigma bonds of spp type, sp of beryllium, and chlorine's p orbital. This side also sp of beryllium and half-filled p orbital of chlorine. 2 sigma bonds are there. So beryllium chloride overall divalent in the excited state because of 2 unpaired electrons. Beryllium undergoes sp hybridization. Only chlorine's half-filled p orbitals overlap with half-filled hybrid orbitals of beryllium and forming 2 sigma bonds. Linear shape, bond angle is 180 degrees. Now boron trichloride, BCl3. Boron trichloride. Boron in the ground state has only 1 unpaired electron. That means it cannot form 3 bonds as given in BCl3. So in the excited state, electrons are promoted to p orbitals in the excited state and 3 unpaired electrons are present here. That is the reason boron is trivalent, forms 3 covalent bonds. In the excited state, it is able to form 3 covalent bonds. In the excited state, boron has 2s1, 2px1, 2py1, 3 unpaired electrons here, trivalent. All these 2s, 2p, 2p, 3 orbitals undergo hybridization, forming 3 sp2 hybrid orbitals. So boron undergoes sp2 hybridization, 1, 2, 3, this pink colored shown, sp2 hybridization, and chlorine's half-filled p orbitals overlap. Chlorine's half-filled p orbitals we have, 3p1, 3pz1, half-filled p orbital of chlorine, overlap with 3 half-filled sp2 hybrid orbitals of boron to form 3 sigma bonds. 3 sigma bonds it is able to form. You can see a sigma sp2p. Here also sigma bond of sp2p. Here also totally 3 sigma bonds of sp2p. What is the bond angle like? 120 degrees. What is the shape? Trigonal planar shape for the overall. Boron in the excited state has 3 unpaired electrons. That is why it is trivalent. In the excited state only, you have 3 half-filled orbitals. They undergo hybridization to form sp2. boron undergoes sp2, and 3 half-filled sp2 hybrid orbitals of boron arranged in trigonal planar shape, and 3 chlorines half-filled p orbitals overlap with sp2 half-filled sp2 hybrid orbitals of boron to form 3 sigma bonds like this. Chlorine has half-filled p. Now boron has 6 electrons in its outer shell in BCl3, so below octet, and each chlorine has octet state in it. Next is methane. Carbon in methane undergoes sp3 hybridization in the excited state, and here it is tetravalent. Carbon is tetravalent here, forms 4 covalent bonds. What is the reason? In the excited state it has 4 unpaired electrons. That is the reason it is undergoing sp3 hybridization and forming 4 covalent bonds. sp3 hybridization. All 4 bond pairs, no lone pairs here. In all this beryllium chloride, boron trichloride also only bond pair repulsions. Only bond pair repulsions. Repulsions are minimum. Geometry is linear in beryllium chloride. Cl3 also bond pair repulsions. Repulsions are minimum. That is the reason why trigonal planar shape. In methane, all 4 bond pairs repulsions are minimum and geometry is tetrahedral. What is the bond angle like? 109 degrees, 109.5 degrees is the bond angle here, and methane. So all are equivalent. See, all have equal strength here, and bond angle is 109.5 degrees. Sp3s, Sp3s. All 4 Sp3s sigma bonds you have in methane molecule with tetrahedral shape. Tetrahedral shape you have geometry and 4 sigma bonds, sp3 hybridization, tetravalent. So overall methane, sp3 hybridization in the excited state, able to form 4 covalent bonds. The reason is, in excited state it has 4 unpaired electrons, and bond pair repulsions are minimum. That is why geometry is tetrahedral and bond angle is 109.5 degrees. All 4 sp3 sigma bonds. Then ammonia. In ammonia molecule, in the ground state only, ammonia has 3 unpaired electrons. In the ground state it undergoes sp3 hybridization, and here lone pair repulsions and bond pair repulsions are there. Lone pair, bond pair repulsions emerge. Though it is sp3 hybridization, geometry in place of, instead of tetrahedra, it is pyramidal shape. Because of these repulsions, lone pair repulsions, geometry takes to the from tetrahedral to pyramidal shape in the molecule. See, pyramidal base of the pyramid. Bond angle is 107 degrees or 107 degrees, 18 minutes. Once again, sp3 hybridization. Nitrogen has 2s2, 2px1, 2py1, 2pz1 in the ground state. The 3 unpaired electrons are present in the ground state. That is why it is able to form 3 covalent bonds. Because of lone pair, bond pair repulsions, though hybridization is sp3, and repulsions of lone pairs cause the geometry to get disturbed. In place of tetrahedra, it has distorted tetrahedra, that is pyramidal shape. This is distorted tetrahedra. Bond angle is 107 degrees, 18 minutes or 107 degrees. So lone pair is at the apex of the pyramid and 3 hydrogens are at the base of the pyramid. This is the ammonia molecule.